Hello, welcome to the OpenBrIM Platform. In the following video, we will show you how to create a substructure local model and set up the model for soil structure analysis. Then, we will demonstrate how to transfer analysis results from the main model to the local model. We will also demonstrate how to use the depth of fixity and equivalent stiffness methods for substructures in OpenBrIM. Let's begin. We need to specify the substructure that we want to transfer in the main project. To achieve that, in the tree view, navigate to Organization, click Organization, then click Cross-Project Data, and then click the Shared Substructure. Click the three-dot menu on the support line and select the support line above the substructure you want to transfer. In our project, we selected Pier 3. You can click the support line appropriate for your project. After selecting the support line, click Add. The project is now ready to transfer objects. Open a new project using the same workflow type as your main project. In this example, the steel-eye girder workflow is used. This will be the local project, which will include the substructure, soil layers, and soil set. In the tree view, let's navigate to External References. This will allow us to reference any model. We will use it to reference our main model. Select Project Objects. Click the three-dot menu and choose Add Projects. A selection box will appear showing all your projects. Select the main project and click Add. Click Shared Objects of the External Project cell, click the three-dot menu, and choose Select Shared Objects. A selection box will appear listing the shared objects defined in the selected project. Select the shared substructure object created in the first step and click Add. The local model is now ready to be created. Click the three-dot menu in any spreadsheet cell in Project Objects and click Sync Shared Object. Then click the Zoom Extent button at the top right. The entire substructure beneath the selected support line should now be visible. You can see in the tree view that all the objects used in the generation of the substructure components have been brought to the local project. Next, we will add soil structure interaction definitions to our local project, such as soil layers and soil sets. First, let's define the soil information that is under the substructure. We will first define the soil layers individually, then define the soil set that consists of these layers. In the tree view, navigate to the substructure and click Soil Structure Interaction. Then click Soil Layer. For the first soil layer, write the name of the layer and press Enter. Select its type by clicking the Soil Type three-dot menu. We will continue with the default cohesionless option. After that, enter the values for unit weight as 102 pounds per cubic foot, top of layer elevation as -38 feet, and bottom of layer elevation as -45 feet. Let's define the second soil layer similarly, with a unit weight of 92 pounds per cubic foot, a top of layer elevation equal to the above layer's bottom elevation, and a bottom of layer elevation of -80 feet. For this project, there are 5 soil layers. We have defined the first 2 layers. The rest of the definitions are copied from Excel. Navigate to the Lateral tab. Available soil models are filtered according to the soil layer type. For example, click the three-dot menu in the first soil layer model. These are the available models defined in the OpenBrIM library for cohesionless soil. You can choose the appropriate model using this menu. For this example, select the Sand Reese soil model. Not applicable cells are controlled according to the selected soil model. After selecting the soil model, you can enter the properties regarding that layer. The Axial tab has an identical input configuration to the Lateral tab. For lateral and axial models, the soil model definitions and their properties are copied from Excel. Navigate to the next tab. To see available tip models, the tip model and its properties are required for the soil layer located at the pile tip. The layer properties that are not located at the tip of the pile may be left as 0. For this example, soil layer 5 is located at the tip of the pile, so only the last soil layer's properties are required. We enter the properties as follows: Poisson's ratio as 0.3, shear modulus as 2.5 kips per square inch, and the ultimate tip resistance as 2,000 kips. Navigate to the Torsional tab. You can specify the properties of each layer. For this example, values are copied and pasted. Now the soil layer definitions are complete. These properties are crucial in the analysis of the substructure since they represent the boundary conditions of the model. In the tree view, navigate to the soil set spreadsheet. The soil set object combines the soil layer objects and completes the definition for soil information under the foundation. Click the three-dot menu under Soil Layers and click Edit. Then click the three-dot menu under the first cell and set the first soil layer defined. Other values are copied and pasted from Excel. For this example, we did not specify different properties for the top and bottom layers separately, so leave the other inputs as default. Then go back and enter the water table elevation. For this example, the water table is entered as -50 feet. The Generate Report input will be explained later in the video. Now the soil set definition is complete and ready to be assigned to the piles. In the tree view, navigate to the substructure, select Pile, and click Pile Layout. In this project, we have 16-inch circular concrete piles with a 3x5 grid setup, 3 piles in the global X stationing direction, and 5 piles in the global Y transverse direction, with equal spacing of 8 feet in both directions. For this project, a pile layout is used to model this setup. However, if your project has a pile instead of a pile layout, the following steps are similar for each object. First, ensure that under the General tab, the pile length and section input represents the actual length of the pile. Click the three-dot menu under the Pile Length and Section cell. Click Edit and change the length if necessary. For this project, the main project's pile length is different, so set it to 120 feet. Next, navigate to the FEA tab to assign soil set objects. Click the three-dot menu under Soil Spring Type and set it to Nonlinear Spring from the soil set. Then, select the section type by clicking the three-dot menu. For this example, a circular section is being used, so select the circular section. This property is used for the calculation of soil curves. Subsequently, under the Soil Springs from the Soil Set Nonlinear cell, click the three-dot menu and select the defined soil set. Other FEA inputs can be determined according to your preferences. For this project, leave them as default. Following this, navigate to the FEA Group Effect tab. In this tab, P-multipliers will be introduced. These values are used to evaluate the group interaction, which is critical for laterally loaded piles. First, click on the three-dot menu of the Assign P-multipliers cell and select Custom. The other two cells are now activated for the X and Y directions. Click the three-dot menu under the X along station input and click Edit. Factors are entered from lead to trailing row, which represent the furthest and closest positions relative to the loading direction, respectively. For this project, values are entered according to AASHTO design specifications. The center-to-center spacing of piles is exactly 3 times the diameter, so for the lead row, enter 0.8, for the second row, enter 0.4, and for the trailing row, enter 0.3. Click Back and click the three-dot menu under the Y transverse direction input, then click Edit. In the transverse direction, the center-to-center spacing is equal to that in the x direction. Again, for the lead row, enter 0.8. For the second row, enter 0.4. And for rows 3 through 5, enter 0.3. Click Back. All data for group effect have now been completed. Please note that pile contributions in the group effect depend on the row position, and the lead and trailing row definitions vary based on the loading direction. Therefore, determining the correct row positions according to pile movement is essential. OpenBrIM can dynamically assign the appropriate P-multiplier during the analysis. This is determined for each pile based on the displacement of the pile head. Before continuing, note that there is a paperclip icon next to the pile layout object name. This means that this object is referenced from another project and will be updated in future synchronizations from the main project. Click on one of the spreadsheet cells in the pile layout and select Disable Sync. The icon is now changed to a lock icon. This means that even though this object is referenced in the main model, synchronizations that affect this object will be skipped. This must be done because changes have been made for soil structure interaction in the local project pile layout, and the main project should not override these changes in future synchronization operations, which will be performed to transfer analysis results from the main model to the local model. Now, all soil structure interaction definitions are assigned to the pile layout. In the 3D view, you should see the generated soil set under the foundation. To see only the 3D view, click the Spreadsheet Close button at the top center of the spreadsheet. The software now generates the curves automatically and assigns the spring properties to nodes. Click the FEA button. Click the Settings button at the bottom left and click View Settings. Ensure that under the Display section, the Supports option is ticked. Close the settings, and the springs assigned to the pile nodes should now be visible. Additionally, it is possible to see generated curves in a report format. Click the Spreadsheet Open button at the bottom center of the page. In the tree view, navigate to Soil Structure Interaction and click Soil Set. Then on the Generate Report cell, click the three-dot menu and change the input to Yes. Now the model will generate the soil set's spring properties report that are assigned to a pile or a pile layout. Click Docs icon located at the left bar, and we see that a report is generated with a combined name of the soil set and pile or pile layout. To open the report, click the name, and after that, click the document icon that appears next to the name. You can navigate within the report by using the tree view on the left side of the page to see the generated curves using soil material properties. For example, click Lateral and click Soil Layer 4. You can see the soil curves are drawn for the nodes that fall into that layer, and the values for the curves are listed below. Using this report, you can validate the inputs you have entered into the software. To close the report, click Back at the top left and click Model on the left sidebar menu. The substructure model is now fully set up with soil structure interaction definitions. In this section, we will transfer the analysis results from the main model to the local model. Before proceeding with this tutorial, please make sure you have a project with completed analysis results. Similar to the transfer of substructure components shown in the previous section, we need to specify the results we want to transfer. Let's navigate to the main project. In the main project, navigate to Organization, Cross-Project Data, and click Analysis Results. And then click Bottom of Column Forces. You can also transfer bearing forces for substructure analysis. However, for this example, we will extract results from the bottom of the column and analyze the footing and piles only. For more details, please refer to the Analysis Result documentation. Click the Column 3-dot menu and select the column that belongs to the substructure of interest. In our example, it is Pier Column 5. Click the 3-dot menu and Extract From. You can either extract results from a result case or a load combination table. For this example, we want to extract factored results, So let's select the Load Combination table. Then click the Load Combination Table three-dot menu and select the Load Combination Table defined for substructure. For this example, we will extract concurrent forces for Strength 1 and Service 1 limit states. In your project, you can choose more limit states. Concurrent forces will be defined in the Force Extraction Settings tab. For now, let's define 12 rows for each limit state. Click the bottom right of one of the cells and drag and drop from rows 1 to 24. Then, under Limit State Input, select cells from row 13 through 24. Then click the three-dot menu. Then click Select and choose the Service 1 limit state. Now navigate to the Force Extraction Settings tab. Instead of extracting all critical results under the bottom of the column, which is an unrealistic scenario, we want to extract the forces maximized and minimized in every direction. That is the reason we define 12 rows for each limit state. Now click the three-dot menu in the first cell under Maximize Force. Then click Select and choose FX. And click the three-dot menu in the Min or Max input cell and select Max. For the first row, the result will be maximum in the axial direction, and the other directions will be the results that occur when the maximum axial force occurs in the column. After that, select the different force directions and maximize force input from rows 1 through 6. The second row as FY. The third as FZ, and so on. You can also drag and drop for the first 6 rows, after assigning the first 2 rows as FX and FY. For the first 6 rows, select Min or Max input as Max. Then copy and paste the same inputs from rows 7 through 12. After that, click the three-dot cell under the Min or Max input cell and select Min. Now we have defined the 12 different result extraction scenarios for the Strength 1 limit state. These definitions cover all the critical cases that can occur under the Strength 1 limit state. Now, let's repeat the same definition for the Service 1 limit state. Select the first 12 rows under Maximize Force and Min or Max input cells. Then click the three-dot menu and click Copy. Then select the Maximize Force input at cell 13. Click the three-dot menu and click Paste. Now all critical scenarios for the Service 1 limit state are defined. Other settings can be arranged as desired, but we left them as default for this example. Let's move to the Extracted Results tab, where we will extract the results before transferring them to the local project. Make sure your analysis results are set before continuing. Click the View FEA button and select Use Previous Analysis Results. After you set your analysis results, select all the rows you defined using only one of the input cells. Click the three-dot menu and then click Extract Result. The results we requested are now extracted and can be seen in the spreadsheet. The results are ready to transfer. Let's click the shared substructure in the tree view. Click the three-dot menu in Transfer Result Extractions and set it to Yes. This allows us to transfer results to the local project. Now navigate to the local project. In the tree view, click External References. Then click Project Objects. In the Project Objects spreadsheet, click the three-dot menu in one of the cells. Then select Sync Shared Objects. In the tree view, click the Project Analysis Results. This spreadsheet displays the information for the results we transferred. The analysis results are now successfully transferred to the local project and are ready to be used for soil structure interaction analysis. The local model can now utilize these forces and moments from the main model for comprehensive substructure analysis. In the tree view, navigate to Construction and click Construction Stage. For this example, we will generate a stage for construction of structures, soil structure analysis related stages, and a stage for each loading. Let's create the first stage. Enter the name as Substructure Stage and press Enter. Leave the other inputs as default. Then, let's create the second stage. Enter the name as Buoyancy Stage and press Enter. After that, click the cell under Prior Stage, click the three-dot menu, and assign the Substructure Stage as the prior stage. For this model, we have a buried footing condition, meaning the footing is below the ground elevation. The vertical loading due to soil should be defined in the model. If your model doesn't have such a condition, you can ignore this step. Let's create a stage for this loading. Enter the name as Earth Loading Stage and press Enter. After that, click the cell under Prior Stage, click the three-dot menu, and assign the Buoyancy Stage as the prior stage. We have completed definitions for construction of structures and soil structure analysis. Now let's define construction stages for the loadings we have transferred. We will define the same number of stages for the loadings we have transferred. Then assign those to a prior stage as the Earth Loading Stage. Let's create a stage named Loading 1. After that, click the cell under Prior Stage, click the three-dot menu, and assign the Earth Loading Stage as the prior stage. Create a second stage named Loading 2. Then, drag and drop the loading stages until the number of loadings you have. For this model, we have 24 loadings. Now, click the Nonlinear Input tab to arrange the stage settings. Under Nonlinear Input, click the header to select all the cells. Then, click the three-dot menu and set Nonlinear to Yes for all stages. Since soil structure analysis uses nonlinear curves as a support spring property, this option must be activated to run the analysis. Other settings in the Nonlinear Input tab can be adjusted according to preference. We leave them as default. Now the stage definitions are complete. Let's move on to the other construction definitions. In the tree view, click Substructure Construction, and then click Foundation Construction Complete. Under the Stage cell, click the three-dot menu and select the Substructure stage. Then, under the Foundation cell, click the three-dot menu, click Select, and select the foundations in the model. For this model, we have only one foundation, so we select one. In the tree view, click Pile Construction and, similar to the foundation construction, select the stage as Substructure Stage. Under the All Piles under Substructure input, click the three-dot menu, click Select, and select the foundation. With these definitions, all piles under the foundation will be constructed in the Substructure stage. Now let's generate the soil structure analysis related loadings. In the tree view, click Loading and then click Loads. Under this menu, we will create loads for the buoyancy effect, buried footing conditions, and apply the transferred forces parametrically. First, in the tree view, click Water Load and then click Buoyancy. OpenBrIM has the capability to automatically calculate the buoyancy effects according to the volume of piles, footings, and pier columns. It only needs to be specified using this library component. Under the Stage cell, click the three-dot menu and select the Buoyancy stage. After that, click the Support Line cell, open the three-dot menu, and then select the support line in the project. Since we defined the water table elevation inside the soil set input, we can assign the soil set to the buoyancy library object. Under the water table elevation input cell, click the three-dot menu and select Use Soil Set Data. Under the Soil Set cell, click the three-dot menu and select the soil set we have defined. Now we have defined the buoyancy load to the model. As mentioned previously, we have a buried footing condition. If your model doesn't have such a condition, you can ignore this definition. In the tree view, click Element Loads, and then click Footing Surface Load. OpenBrIM doesn't automatically calculate the weight of the soil above the footing. It is the user's responsibility to calculate this loading according to the volume and unit weight of the soil. The loading can then be assigned under Footing Surface Load. Under Footing, click the three-dot menu and select the footing. After that, click the Stage cell and select the Earth Loading Stage. For this model, we calculated the loading as 0.204 kips per square foot. Since this loading is in the gravity direction, enter the value under Force in Z direction. Let's move to the final loading definition to analyze the model and define the transferred loadings to the model. Since we constructed the footing and piles only, we have to apply these loads to the footings. In the tree view, click Footing Point Load. Under the Footing cell, click the three-dot menu and select the footing that the load will be applied to. Then select the stage as Loading 1 by clicking the three-dot menu on the Stage cell. This is the stage where the load will be applied. After that, we need to reference a location for the point load. We will reference the column center, so under the Specify Position As cell, click the three-dot menu and select Column Center. Then the column cell is activated. Click the three-dot menu on the column cell and select the column that the forces were extracted from. Now let's define other loading rows. In the second row, click under the Stage Input, click the three-dot menu and select the Loading To stage. Now we can drag and drop for all of the remaining stages. Now we need to input the results we have transferred. We can define these loads parametrically, so if there is any change in the main model, the values are updated with a simple synchronization. In the tree view, click External References, then click Project Analysis Results. We transferred these results previously. Now select the 6 results columns and all rows. Click the three-dot menu and select Copy Parameter. Now we have copied the references to these cells. Let's assign these loadings to the structure parametrically. In the tree view, select Footing Point Load that we have just defined. Click the three-dot menu on the cell under Force in X direction and select Paste. You can also use Ctrl-V. Now, as you should see, the function icon appears on the bottom left part of the cell. This means we have successfully defined the loads parametrically. So if any change happens in the main model that affects the results, what we need to do is click External References in the tree view, select Project Objects, then select any cell in the spreadsheet and click Sync. In this section, we will demonstrate 2 methods for representing substructure stiffness in the main model. The first is the depth of fixity approach, and the second is the equivalent stiffness approach. The aim of this section is to show how to determine the depth of fixity for the pile and assign that value to the main model to represent substructure stiffness. Using this method, the foundation is idealized with a simpler approach without requiring nonlinear analysis in the main project or iterative processes between the foundation model and the main model. To determine the depth of fixity, we will examine the moment diagrams of the piles. To do this, switch to the Finite Element Model view by clicking the FEA button. First, click the Spreadsheet Close button to view the results clearly. Then, click the first drop-down menu and select Composite Forces. A pop-up menu will appear. Select any one of the piles, since the moment diagrams of the piles will be similar, and selecting any one of them is sufficient. For display purposes, we selected the first pile. Then click Show. Next, select the critical construction stage for the pile using the drop-down menu at the bottom. In this case, the critical stage is Loading 6. Then select the critical moment direction, which for this model is MY. We can increase the scale to see it more clearly. Next, focus on the second inflection point on the graph. This point represents the depth of fixity, where pile movement approaches zero. To identify the 0 point more clearly, zoom in on the second inflection point. You can rotate the camera by holding the left mouse button. In our model, this point is located near node 13 of the pile, at an elevation of -106 feet. This is the depth of fixity for this pile layout. We can also calculate an axial stiffness value at the depth of fixity for use in the main model. To do this, divide the force by the displacement at the depth of fixity. Hover over the element above the depth of fixity node and identify the force at node 2. In our case, it is 182 kips in compression. Then read the displacement at node 13, which is 0.18 inches. The stiffness can then be calculated as 1,011 kips per inch. Now navigate to the main project. Go to the Pier column by clicking Substructure, Pier, and Pier column. The bottom elevation is -40 feet and the footing thickness is 6 feet. Therefore, the bottom face of the footing is located at -46 feet. This means the pile tip location from the face of the column is 60 feet. Next, navigate by clicking Pile and Pile Layout. For the substructure we are working on, which is Pier 3, click the three-dot menu in the Pile Length and Section cell and click Edit. Then update the section length to 60 feet. Then navigate to the FEA tab and click the Soil Springs Linear cell. Open the three-dot menu and click Edit. In this depth of fixity approach, our objective is to replicate the behavior of the nonlinear model with respect to axial load distribution in the piles, allowing us to evaluate within the main linear model whether the pile capacity has been exceeded. The most critical factor is matching the stiffness at the pile base to achieve comparable overall behavior. In addition, releasing the piles in the lateral direction can lead to significant discrepancies in lateral response and displacement within the main model. Therefore, applying a similar approach laterally and assigning comparable stiffness values to the nodes between the pile head and base can improve consistency between the two models. For simplicity, in this example, we will introduce a nominal stiffness of 10 kips per inch at all nodes above the pile tip. For the tip node, we define every degree of freedom as fixed, except for the TZ stiffness, for which we enter the axial stiffness value calculated earlier, 1,011 kips per inch. Following these definitions, we will open the model that has been prepared to display the analysis results after these changes. We can then compare the axial load distribution at the pile heads in the main model. Examining the Strength 1 limit state results at the pile heads, we observe that the distribution of axial load is similar across the piles. The stiffness of the substructure is represented in the main model using the depth of fixity approach, based on the refined soil structure analysis results from the local model. Let us now move on to the equivalent stiffness section. The goal of this section is to show how to determine the equivalent stiffness of the footing and pile, and how to assign that stiffness matrix to the main model to represent substructure stiffness. In this approach, the substructure stiffness is represented at the bottom node of the column, or at the center of the footing if there are multiple columns. The piles are not modeled in the main project. Instead, the substructure stiffness is represented by a 6x6 stiffness matrix. To extract the equivalent stiffness at a given node, we must first select the node at which the equivalent stiffness will be extracted before analyzing the model. Make sure the FEA view is active. To activate it, click FEA in the menu on the left. Open the FEA workflow and click Result Combinations in the tree view. Then click Equivalent Stiffness. Click the spreadsheet cell under the Name column and enter a name. Then click the next cell, open the three-dot menu and click Pick Nodes. In our case, we will select only one node at the center of the foundation. The equivalent stiffness will be generated at this node location. Click the node, then click Done at the top. Now we have selected the node for the equivalent stiffness extraction. To generate the equivalent stiffness, we need to analyze the model. During the analysis, the stiffness is calculated for every stage and saved. Click the Analyze button. After the analysis is completed, click the Close button. In the same spreadsheet, open the three-dot menu on the row we created, then click View Stiffness Matrix. In this tab, you can see the equivalent stiffness matrix generated at the selected node. Now select the critical stage and view the stiffness matrix. For our case, the critical stage is loading 6. We are now ready to assign the stiffness matrix to the main project. First, select all the cells that contain the stiffness matrix values. Then open the three-dot menu and click Copy. Now, in the main project, we will assign the stiffness matrix to the column object. Now navigate to the main project. In the main project, click Substructure, then click Pier and Pier Column in order. The pier columns are listed in the spreadsheet. We are working on the foundation under Pier Column 5, so we are going to modify the FEM properties of Pier Column 5. If you have multiple columns on top of a single footing, you need to assign the stiffness matrix using the foundation object. The assignment process is similar. Let's activate the FEA view from the menu on the left so we can visually see the effects of the changes we made. Click the FEM category and navigate to the cell under Bottom Fixity for Pier Column 5. Open the three-dot menu and select Stiffness Matrix. The 6x6 stiffness matrix cell will become active. Click that cell, open the three-dot menu, and click 6x6 stiffness matrix. We can paste the values we copied previously by pressing Ctrl-V. Then click OK. We have now successfully assigned the stiffness matrix beneath the column. Next, we need to deactivate the FEM on the footing. Navigate to Foundation in the tree view and click Rectangular Footing. Then under Generate FEM column, click the cell and select No. Now, in the Finite Element view, we can see the changes. Hover over the node at the bottom, and you can see that the 6x6 stiffness matrix has been assigned to the bottom node of the column. The stiffness of the substructure is represented in the main model using an equivalent stiffness approach based on the refined soil structure analysis results from the local model. Iteration between the main model and the local model are required to arrive at the correct stiffness values. These iterations can be performed very quickly in OpenBrIM by using the sync feature between the linear main model and the local nonlinear soil structure interaction model, which was demonstrated earlier in the video.